All right. Well, thank you very much for joining today. My name is Daniel Novak. I am Director of Student Scholarly Activities at the University of California, Riverside School of Medicine. This is week 4 of our TriNetX Summer 24 Boot Camp for 2025, rather. And we're going to be talking about conducting outcomes analyses today. For those who've been following along, this is the fourth, and this is kind of the most exciting or the most interesting one because we're finally getting to a place we can start to look at actual statistical outcomes. And today we're going to look through all of the different kinds of statistical tests and information that's available in TriNetX that will allow you to conduct a really thorough and good quality analysis of the data. As always, through the boot camp, you're going to learn about navigating TriNetX, identifying worthwhile projects, comparing outcomes between patients, and using propensity score matching to reduce confounders. We talked about propensity score matching at length last week, and we're going to just revisit that a little bit. On the way through our sessions, this is kind of the overall structure of our series, and we are now in week 4, looking at our outcome statistics. We are looking at ways to understand or to know whether what we're seeing is actually accurate or not. We're going to be looking at statistics and trying to understand the population statistics that are in there. For those where you may need a little bit of a refresher on evidence-based medicine and epidemiology and biostats, we'll be covering some of the key concepts here as well in detail. If you're following along with our TriNetX rapid development process, we are generally in the generate initial outcomes and rebuild your cohorts if necessary component of it. And if you're doing the even more rapid process, you should be examining your outcomes and checking them with an expert as you go as well in steps 7 and 8. In my clunky metaphor of TriNetX, we've completed the foundation by doing good literature reviews, created good cohort inclusion and exclusion criteria, time and order effects, and cohort exploration for confounders. We have built our structure of our house, which is choosing good analysis type for our project, cause and effect order, and propensity score matching. We covered this a lot last week in the last session 3 last week. And now we're building our outcomes. We're putting the roof on our house and making sure that it's nice and sound. So looking back at our example summary of this guy and his clownery, he's a social media person who gives very questionable medical advice, and he claims that Alzheimer's disease is a physician-created condition that didn't exist even 40 years ago, not even under another name. I believe he specifically says that. Statins, specifically overprescription of statins, is causing the surge and the increase in it because of it messes with cholesterol metabolism in the brain. Brain is very full of cholesterol compounds and derivatives that are necessary for good health. And none of this is correct. None of this is medically sound or accurate. Or rather, there's enough truth in there to make it sound correct, but it's really not. I mean, based on the best science and peer-reviewed literature that's available from multiple global experts on the subject. Alzheimer's is a very complex disease with lots of different causes and factors. And statins were identified decades before. Alzheimer's didn't exist, also not under another name, 40 years ago, and exponentially increased with systemic abuse of statins and fear-mongering of cholesterol. I mean, yes, there has been fear-mongering of cholesterol, but Alzheimer's has been around since at least 1906, and even further back into the 1890s when it was identified. And statins weren't produced until 1987, 81 years later. So I'm expected to believe that Alzheimer's didn't exist in those 81 years. Fat chance. So, even clowns on the internet can have important ideas that need to be addressed or thought about. So scientists and physicians have been looking at whether we are potentially overprescribing statins across the board. Now, they weren't looking specifically at Alzheimer's and the impact of statins on Alzheimer's, though there is a deep literature on that we've been following and that I described in one of our earlier sessions, but it is an impact that we want to assess. Again, it's complicated. Statin dosage that could be at play. There's length of treatment, comorbidities, dietary considerations. Everywhere you can show, there's a very compelling graph that shows everywhere in the world where beef consumption goes up, Alzheimer's goes up right with it. Is it a correlation? Is it causal? We don't know. Poor understanding of Alzheimer's causes as well. I mean, what is it a type 3? There's the diabetes type 3 hypothesis. There's neuroinflammation. There's glial cells involved. Lots and lots of complicated systemic issues, along with age as a confounding factor. There's also genetic issues. People with ApoE3 and E4 with these genetic alleles wind up having Alzheimer's much earlier with much more severe symptoms, much faster. So there could be a genetic dimension that no amount of statins could prevent. Or alter the course of that disease progression. Then there's also, as I always point out, an ethics issue. If statins help with triglycerides, that could lead to stroke or blood vessel claudication or all sorts of stuff like that. Is it even ethical to withhold that to protect people from the possibility of Alzheimer's, right? And we don't know. And we just don't know a lot of these things. There's been decades of research on it with inconclusive results. So as I said earlier, the recent meta-analyses do indicate that things are, when you look at either randomized controlled trials or observational studies, you can find that there are really varying assessments of risk for these groups as well. So TriNetX is a really great tool for looking at this because it's very difficult to study these issues over time, especially over the length of time of the development of Alzheimer's, from something that might not be picked up at a doctor's office to something that gets a formal determination, a formal assessment. The disease progression changes for different people. We don't always know. So a large real-world data set like TriNetX would allow us to assess how frequently this is occurring in the field and what's going on. So we're running our hypotheses. Statin use is associated with a lower likelihood of developing Alzheimer's disease is our thought, because that's kind of where the research is pointing in some cases. Just a quick review of what we were looking at last time. The characteristics window, we're going to look really quickly at our index event and how this is defined. Index events I talked about at length in session 3. A really important concept to understand. The index event is the first day in which all of the characteristics of your people in the study are true. And we can set how far back we want, using the characteristics window, how far back we want to look in the patient's record. So the first day that they had asthma and were given dupilumab or something like that, we can look and say in the last 5 years, right, as well. So this allows us to set a backwards look at our folks using our time machine. We can peer into the past of the person's health record. And that index event allows us to relate cohort characteristics from the past to outcomes in the future. Again, we can't make causal inferences, but we can make more and stronger and better correlational influences based on that as well, or measures of associations, we might say. The index event for each patient is the day on which the patient first met all selected criteria for the cohort. Please, if you get a chance, review this example on the TriNetX website, and I talked about directly in session 3. It's very important to understand this concept very thoroughly. It's not necessarily intuitive just by looking at TriNetX kind of assumes you understand this concept already before you get started. So now a reminder to review your cohorts. So separate from your propensity score matching features, we're going to look at a feature today that allows you to, or rather, we're going to look at how you save characteristics for your groups and how your baseline stats tools can provide a thumbnail comparison of rates in the 2 cohorts overall. This isn't as nuanced as your outcomes analysis, but it can tell you if you should consider propensity score matching more strongly, or if you should review your cohorts to exclude a factor. You can see here that when you are starring these characteristics to add them to your propensity score model through the demographics, diagnoses, procedures, medications, and labs, doctors don't pay money late. One of our students came up with that mnemonic. That is where your that allows you to add those characteristics there so you can baseline analyze it. And so using the baseline comparison statistics tool that is in your outcomes analysis tool within TriNetX, you can use these tools to give you just a quick t-test, or it's actually a z-test, but comparing the groups and letting you know whether there is a statistically significant difference between the two. So between our two groups, there is a slight statistically significant difference in one group and the other. Now, this is completely not propensity score matched or anything like that. This is just looking to see whether we could assess the need to propensity score match for each of these individual files. So for each of these individual groups. Again, just to revisit really quickly, propensity score matching is an essential feature of your work in TriNetX, because if you don't use propensity score matching to help balance some of your cohorts, what you can wind up with is a situation where you're not really seeing the differences between the cause and effect relationships that you're looking for, whether a medication improves outcomes for people. All you would be seeing is whether older people get sicker faster, or whether younger people are at higher risk of having fractures, which is often the case, depending on what you're looking at. So those are, if you're not propensity score matching, in, for example, just by age alone, you're missing out on a lot of the different kinds of variance, controlling for a lot of the different kinds of variance that might be impacting your data and leading you to a wrong finding. Again, it's a statistical technique where we construct from your big pools of people that you've selected, we select two sub-pools that are not statistically significantly different from each other based on the characteristics that you define in TriNetX. You can please review video 3 if you have more questions about it. And there's a lot of nuance to it. TriNetX provides some really good, useful information on it. This just shows you, again, the graphs that you'll see showing how much of an overlap there is between the two groups, how likely, how much of a propensity there is for one group or another, or sorry, for one individual to belong to one group or another. And by, you can see in the graph on the left, there's actually a lot of differences in the scores of the people based on the characteristics that I chose for this study. So there's not a lot of overlap between the two groups. After matching, taking that subpool of 168,000 people out of the larger pool of 3 million non-statin exposed people, and comparing that to the statin exposed people, taking a smaller slice of the 169,000 people in there and comparing those groups, the 168,795 random, not otherwise random, but like not statistically significantly different people from group 1 compared to the 168,000 not statistically significantly different people from group 2. Comparing those allows us to see that there's a much stronger overlap between the two now, and that the degree of randomization is a lot higher. So that was what we covered in week 3. It's really important to go back and make sure you have a very strong understanding of that concept in order to kind of proceed on in the analysis. So this week, we're going to look at the concept of exploring outcomes. This is a really, really useful feature because a lot of times people go and they build this whole study out and they look at it, and it turns out that there's only like 12 people who have ever experienced this hypothetical outcome that they're looking for. And that can be, really disheartening to put in so much work and to find that your outcome is just so rare that you can't really make a lot of statistically generalizable claims about it. So one way to kind of avoid this is to use the exploring outcomes function to just see, before you start running, have you caught the right outcomes that are different between the groups? Can you see whether these outcomes, whether there are going to be enough people in your analysis after you've both propensity score matched and even before, this all occurs before propensity score matching, but to make sure that you've got all the right people identified early on. So this tool is really useful. So let's go through it a little bit. You'll see that the window looks just like the characteristics, but a key difference is that it explores all outcomes in the future. The characteristics looks into the cohorts past. The exploring outcomes compares all diagnoses, procedures, medications, labs going into the future. It just compares everything against everything in both groups. It's a great way to determine if you're going to have enough people. And that can help, again, with avoiding or spotting rare or unusual situations that could be potential confounders. And you can check to make sure that you've got all the right procedural codes and medications in your cohort. You might find that by looking at comparing both cohorts along all lines, that you're missing a potential set of CPT codes or ICD-10 codes that could add a lot of people to your study and give you greater statistical power in the particular research question you're looking at. But I want to be mindful that this is not suitable for your final analysis. It's a great way to find unexpected outcomes. The outcomes in your cohort can then be easily added to your final analysis. I'll show you how to do that in just a sec. But basically, in the same way that our time machine took us into the past for the characteristics, as I said, the exploring outcomes takes us into the future. It allows us to look from the same day all the way up to the end of the patient's health record, which is really useful for a lot of reasons. As I said, it operates on the same doctors don't pay money late framework as before. You can see that defined over here. Here's the diagnoses, procedures, medications, labs, and genomics for all people in the study, all your 3.9 million people, almost 4 million people in this study. So the first thing you can look at in this, once you have run your compare outcomes and it loads, is your diagnoses. And you can see that the diagnoses are grouped, comparing all cohorts going forward in terms of who's likely to get these outcomes. But it's grouped by, you can choose to limit it by all acute conditions or chronic conditions, depending on what kind of research you're doing. And you can see it'll show you just, every ICD-10 code and how many are present in each group of people. You can search for specific findings to help make it easier to get, down to G30 really quickly. And then the same signal and star icons that we saw in the characteristics function in last week are also present here, except they work a little differently. They add your outcomes here to a saved outcomes folder. So instead of going to your propensity score matching, I want to be clear, this goes into the future to allow you to quickly pull this in to your final analysis. So by using this compare outcomes thing, you can star a bunch of stuff and add it to your final outcomes analysis later really easily. Yeah, so that's your compare outcomes tool, or your explore cohorts tool rather, and that will allow you to see what's going on in there, exploring your outcomes really easily. But we're going to move on to the main event. The main thing that we're interested in is running outcome stats. This is it. We're here. We have done it. We've selected our covariates for our propensity score match. We've identified our outcomes. We're finally ready to find out our results. We have done it. We've thought so much that our study is really beefy and strong. So what I want to do really quickly, though, is give you a couple of guiding decisions that you're going to have to make to get the best analysis possible. Afterwards, we're going to talk about the stats really clearly. But I want to give you some thoughts about decisions you have to make as you're running your analysis. The first and most important decision is propensity score matching or no propensity score matching. You can turn that option on and off in your analysis tool really easily just by clicking this button that says select balance preference. It doesn't tell you anything about propensity score matching, but compare cohorts before matching turns it off. Comparing cohorts after matching turns it on. And that allows you to then load all of your characteristics into the statistical model and have them used to select the people for your analysis. So that turns your propensity score matching on. Reasons to propensity score match, you should consider if you have a large and heterogeneous group of people, lots of random chance in there that's messing up your analysis, and you really are just finding out that cancer patients have higher rates of infection than non-cancer patients, and that's not really what you're actually asking. You could have lopsided cohorts. That is, one is very small, 3 million people in one and 50,000 in another. The problem with that, again, is using an effect control model for this can be a reasonable idea. It can be the only way to answer some of the questions you might have. However, the amount of random chance in those very, very large cohorts versus very small cohorts might mean that propensity score matching is essential to helping you reduce the amount of random variation in your group. And you might also have identified confounders or demographic differences that need to be controlled for in your study. And please review the differences between mediators and confounders in your study and in session 3. That will help you understand whether and how to use propensity score matching optimally. But I do want to correct some common mistaken thinking. I hear this stinking thinking from students and faculty all the time, and I want to just dispel this. So firstly, some people will say to me things like, propensity score matching makes my cohorts too small. Having a large cohort of random unconnected people is not a good way to get to a scientific study. Propensity score matching makes your cohorts, if you do it correctly and you do it with the best possible knowledge that you have, given that there's some potential, the researcher's knowledge itself is a potential confounder for selecting those propensity score matching characteristics. Having a smaller propensity score matched cohort should provide you with a more accurate version than having a large group of random people in there. So making your cohorts smaller is not a bad thing. It's not the size of the cohort, it's who's in it, and making sure that they're the right people to answer the question that you're asking. Number two is people will say, well, before matching, my results were statistically significant, and after matching, they're no longer significant. Maybe I shouldn't propensity score match, just report my unmatched results. Nobody will know, right? And I'll have these beautifully P is less than 0.05 answers, right? No, that is not right, because if you are, if your propensity score matching changes the statistical significance of your findings, what that would indicate is there is some confounding factor there that is making your statistic, that is influencing the significance of your group, and you don't want to do that, right? You don't want to publish wrong results, right? And also, any reviewer worth their salt is going to ask how you controlled for different kinds of variance, right? The propensity score matching thing, if it means your study is not statistically significant after using it, and you did the propensity score matching correct, and it all makes sense, it might indicate that one of your factors is catching that before you write up a whole manuscript and submit it, and then people just reject it because it's inaccurate and they have questions about it. So using propensity score matching when it's a good idea and when it works, and you've done a good job on it, really, 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 really helps to ensure that your scientific research is top-notch. So do that. People say also, I don't really understand propensity score matching. I'll just throw everything into it and it'll be okay, right? And I'm like, no, you don't just select everything and match for everything, because then you're matching for nothing, right? It's a theory-driven approach that helps you to leverage your knowledge of clinical medicine and biomedicine and all the different aspects of clinical care and sociology and everything that is health, and to use that to identify factors that could be impacting your group and removing it. Putting in propensity score matching, as we talked about last time, for top-level codes like all cardiovascular disorders. Well, the problem with that is that cardiovascular disorders category, the ICD-10 codes for that, includes everything under the sun and can really mess up your analysis if you don't do it correctly. So it's really important to understand how propensity score matching works. Please watch the video. I tried to explain as best as possible, and always happy to take you through it individually if you need help. But don't treat it as a random exercise or a throwaway exercise. It's really important to understand and do properly. Next up, a decision that you really have to make is about time frame. So when we're looking to the future, that's great, right? We can see as far into the person's record as today, and we can see, in some cases, 20 years of a person's record in TriNetX, which gives you a really good snapshot of their health span. We go back to the future, but when selecting your time frame for the study, you really have to think about the longer your time frame first, the less likely that your outcomes are related to the event. Temporal relationships are really essential to factor in TriNetX, because when just as people get older, they're naturally more susceptible to disease and disorders. That's just a fact of mortality of life, right? Of being immortal. And that is a thing you need to think about as well. So if your study if every single one of your outcomes is a 25 or 20-year outcome, well, who knows what's influencing that in that time frame? If you're looking for 20-year rates of depression, well, in 20 years, people can lose loved ones, people can have neurochemical changes unrelated to your situation that you're interested in. They can have all sorts of stuff going on with them. Medications change over time. Standards of care change, assessment techniques change. So the longer your time frame, the harder it is to establish causal, or not causal, but temporal relationships between them. And that's a problem. On the other hand, picking too short a time frame means that you might miss the outcomes that you're actually interested in because, if you're looking at a 2-day time span, but the amount of time it takes for things to occur is 6 months, well, that's a problem. Then one example of this is related to postpartum outcomes for women, right? So in the past, they would look for 90 days to see bleeds and hemorrhages and things like that, and C-section damage or postpartum depression. But now they're starting to understand that it can take much longer for these things to unravel than you might think. So that can be really challenging to manage. But to manage these issues, to determine the right time frame, first consider the type of disease and condition. Cancers take longer than infections to see an impact. Some can take years and some can take days, right? Something to factor in. Consider existing research. What kinds of timeframes are used in other studies? For example, is it a 5-year trial, 10-year cancer outcomes, 7-year cancer outcomes, whatever that may be? Another way, if you don't know and don't have a lot of guidance from the research, is to use the Kaplan-Meier tool in there to see if you need to zoom in. So you could look, starting out with the whole lifetime, as long as those records are, and then zoom in and say, well, 90% of my cases of this thing that I'm seeing on my Kaplan-Meier curve take place in the first 3,000 days. And after that, kind of drifts off, right? So you might say, well, okay, then it's likely that this could take 3,000 days. That should be my length of time for the study. Or you might find that almost all of your cases occur right away, and then they kind of drift off over time. Well, you might want to then change your time frame to catch most of the people with the most proximate outcomes. So something to think about. Just a pro tip for multiple time frames is once you've set up maybe your lifetime one or whichever one is your kind of primary analysis, if you want to run multiple different ones, you can duplicate your analysis and change the time frame instead of having to take your analysis, run it once, copy out all the numbers, change the time frame, do it again. You can copy these multiple times and have a 7-year, a 10-year, a 20-year version, and run them all in parallel if you want to do it that way. You can run them in multiple browser tabs at the same time, so you can run it pretty quick when you need to, if you need to update them. The only challenge with doing it this way is if you make a change to one, you have to propagate that change to all the other copies as well. So I generally tend to recommend getting your cohorts, your propensity score matching model, everything as perfect as you possibly can before you start to clone it out for different timeframes. Leave that analysis for last. Another decision you have to make is index events. Are all of the characteristic of the cohort index events, or are some of the factors not part of the index events? That can be really important to understand. This can impact your outcomes by impacting when patients enter the study. So you might, of course, want to have some feature of one of your groups be a cohort defining feature, but it might not impact when the study starts. It could be either so distant in the past that it's not relevant to your current study, but you do want to make sure that the person, for example, had a cleft palate as a child, so you include that, the surgical codes for fixing that. But what you really want to know is about medications and depression later on, unrelated to the cleft palate. So that could be something that is not part of your index event because it definitely would have happened before your secondary events. But you can choose that using these little blue boxes next to each group. Generally, you can just add everything as part of your index event, but there may be situations where you don't need everything to be the defining feature. The next two decisions you're going to have to make come in the outcomes area itself. This is where you're going to start adding in your specific outcomes that you're looking for. You can have as many outcomes in the outcomes analysis tool as you want. You can do 25 outcomes, one after the other. You can pool outcomes together. So you could have all cause dementia or something like that if you wanted to do something that way. But in this case, I'm looking specifically at Alzheimer's disease, the top level code for it. So that makes decision number 4. Do we want to pool our outcomes? So I'm looking right now at decision at G30. I could do it that way, but you could also do something pooled where you've got all of your outcomes added. So you could have Alzheimer's and Parkinson's and other degenerative nervous system diseases all thrown together into one soup. There is no way to use Boolean logic in your outcomes analysis tool. It's going to be this condition or this condition or this condition or this condition. There's no and function. So pooling them together really only allows you to see whether they have one of these. If you need to know more specifically which ones they get, you're going to need to use the individual outcomes like this. This again is where I showed you a little while ago when you are in your explore outcomes function and you star one. This allows you to pull in this menu in TriNetX, allows you to easily pull in your identified outcomes from there. So you don't have to go and remember a bunch of ICD-10 codes. You can just tag them all with stars in your explore outcomes function that we saw a moment ago, and then load them in very easily. As I said, you can't use AND connectors, so you have to be very careful about that. Again, a couple of trade-offs. Single outcomes may underestimate your findings because you might be missing effort, multiple outcomes or factors that might be of interest to your research question. And pooled outcomes, though, can confuse your analysis since you can't see a breakdown of which people belong with which outcomes or what percentage of each group got a sub-outcome. So that's a decision you have to make as you go. Decision 5, exclude cases with prior outcomes. This is a checkbox. It's a very important checkbox next to your measures of association, your Kaplan-Meier analysis, and your number of instances. This checkbox over here, basically, just going to highlight it over here. This checkbox essentially excludes anyone with Alzheimer's from our study if that Alzheimer's diagnosis had come before the index event date, the date that the person's indexed into our study. So that means that anybody who had statins for less than a year, anybody who had never had statins or anything like that, but developed Alzheimer's, they would be excluded from this study before we even begin. So that's really, really, really important to know, and it's very important to use this tool wisely. It can save you a lot of time, which is great, but there's a caveat to it. So the TriNetX people informed me when they came to visit for our Dean's Research Day last year that the exclude cases button can limit cohort or can save a lot of time in cohort complexity because you don't have to go back and redefine your cohorts as excluding people with Alzheimer's or any other outcome prior to all of the other factors that you really want. It can just be really annoying to have to go back and set that up for every cohort you work on. However, if you do that, it excludes people after propensity score matching. The reason that's so problematic is the people in your study won't be replaced after being ejected, right? So you're doing your propensity score matching, and then you have a couple of people, let's say, we'll take an example here. Your cohort 1 has 10,000 people in it, and your cohort 2 has 1,200 people in it. You're comparing a relatively large cohort to a relatively small cohort. After propensity score matching, you've been able to capture 1,180 people in each group, but one cohort 1, has 500 people with the outcome prior to the study, and cohort 2 has 300 people prior to the outcome with the outcome prior to the study. So because it removes people after matching, you're really comparing 700 people from cohort 1 against 900 people in cohort 2. And that can make a really challenging issue for you in the sense that it's just really gonna reduce the amount of statistical power that you've got for 2 such small cohorts to begin with. Again, not necessarily bad because those people were not helping us with our study, but because they were brought in to propensity score match, then kicked out after finding out that they had this outcome prior to the window, you lose those extra, in one case, 500 people, and in the other case, 300 people from your overall random pool of people that it could have drawn from. And that makes a problem that if you go back and exclude those people beforehand, you get 900 people in both pools and a much stronger study coming out of that. So if you have a small set of cohorts, excluding people post-match can reduce your overall cohort sizes and mess up your numbers a little bit. So that's just something you need to decide on early. So one way to know whether you should exclude in your outcomes or in your cohort, that is go back and redefine your cohort or not, is to look at your cohorts here. You can see underneath any of your measures of analysis that we're going to look at in a minute, after you run your TriNetX study with propensity score matching on, you can see in this example, I lost 853 people from cohort 1 and 3,030 people from cohort 2. Now, that's out of a total of 1.076 million and 29 matched into both cohorts in the one-to-one matching process. So I'm not really worried about losing those people. Number one, they weren't people of interest for me anyway. Number two, there's still over 1 million people in each group, right? That's great. That's plenty of statistical power for the study that we're looking at. But if you lose more than enough to shift your numbers, you might want to consider going back to your cohort definition. So this is one where I actually have to think about, be like, okay, well, I lost 3,000 Alzheimer's patients from here. So do I want to go back and redefine my cohort so that if I kick those 3,000 people out beforehand, I could capture a bigger chunk of a randomly distributed 3,000 group of people who might have had Alzheimer's after the index event, and those people would contribute to my actual patients with outcomes over here instead of just getting lost. So something to think about as you're making decisions and trying to come up with the most accurate possible study. Okay, you've made your decisions, you've run your cohorts, you've redesigned your cohorts, you've got your initial outcomes, and you're going to run it. Now we're prepared to run our analysis, and I am going to turn propensity score matching on for that one as well. So let's look at your outcome stats. This is going to be a little biostats heavy, so if you hate biostats, well, that's tough. Your types of stats. First, we're going to look at your propensity score matching results for outcomes. We're going to see what those look like in mean again. We're going to look at your measures of association, probability, risk ratios, odds ratios, and z-tests. We're going to look at your Kaplan-Meier curves, which is related to time. That's your log rank test, your hazard ratio, and your chi-square proportionality. And we're going to really briefly look at number of instances because I don't really use it very much because it's not that useful for the work that I do and for the work that most of you would do. First, we're going to look at propensity score matching results. So the first thing you're going to see when you get to your results on your studies in TriNetX is a graph that looks like this weird squiggle over here. And basically what this tells us, as I mentioned earlier, is whether there's a lot of propensity for one particular group of people to be in one group versus the other. And you can see that my purple group, my statins group, there's a lot of propensity to be in that group. There's a lot more illness. There's a lot more random characteristics that are impacting them. After matching, though, there's not really a lot of propensity for people to be in one group or the other. We've controlled for a lot of characteristics, so there's a lot of overlap in this graph between our two groups. TriNetX does not produce value that would tell us the quantitative, the actual number, but we can see generally over here that the graph indicates that things are pretty they're pretty randomly distributed. The likelihood of being in one group or the other is roughly the same for most of the groups across most densities of the cohorts. So let's just take a look quickly at how to read these tables again, before and after matching. So what you can see here is that before matching, each group was statistically distinct. What that means is that they were statistically significantly different, which is a bad thing. It's the only time this is ever bad in research, is that because they were statistically significantly different, it means that there's some factor, in this case, age, we're looking at. This age factor is different between the two groups. The distributions of ages are different between the two groups. So I'm going to jump back to that. That's bad for our purposes because it means that what we're seeing is partly the results are just because this group is 13 years older. Our statins group is actually 13 years older on average, plus or minus 11 years than our non-statins group. So that amount of variation can really, really mess up our analysis. And you can see this, by the way, there's these two boxes to turn on your p-value and standard difference. When you do that, that's actually really important to do. So you can check out these numbers. So after propensity score matching, though, you can see that our numbers are no longer statistically significantly different, which is great. Why is it great to get p is greater than 0.05? Well, it means that there's no difference between the groups. Let's say there's no systematic statistically significant difference between the groups, and that the standard difference in each group, the likelihood of those things occurring in each group is less than 0.1. Less than 0.1 is actually really important. This is particularly true of well, I'll actually explain in a second, but just to recap, before matching, you want your covariates to be statistically significant. If they aren't, that means that you can probably remove that factor from your model because it can cause overfit. It can distort the amount of variance isn't allocated correctly. So if the two groups are already statistically significantly different before matching, don't try to make them don't include them in here already. Propensity score matching doesn't need to be done on those two groups or based on that characteristic. As I said, after matching, you want them to be and to not be statistically significantly different, and that's counterintuitive because that's different from what we look at so much everywhere else. What I was saying a moment ago, we want to zoom in on the idea of these large cohorts. You might be working on a cohort that has hundreds of thousands, if not millions of people in it. So if you're working with these large cohorts, it's almost impossible to get a statistically non-significant value since really minor differences and variations in the distributions can be read by the z-test as statistically significant differences. So in this case, we were able to achieve that, but one way that you can know when this happens is to use the standard diff value. If standard diff is less than 0.1 for a group, that means it's sufficiently randomized. That means that there's statistically no significant, or that there's no significant difference between them. And you can see here that that's the opposite is true in the before matching because the p-value is statistically significant before matching and the value is greater than 0.1 for those as well, and greater than 0.1 over there. So that's one way you can know, even if in your study, if you have a very large group of people, standard differences can tell you, even if you're there, if propensity score matching, after propensity score matching, they're still statistically significantly different, your p-value, your standard difference can fix that. So that's propensity score matching for your outcomes. We're going to talk about 4 important values, though, going forward into your measures of association, which is one of the primary reportable components in TriNetX that's interesting. The first is the concept of risk difference. And one thing I want to share with you is when to use each of these numbers in your studies. So risk difference is great because it's the absolute effect size. It's how much of a difference, how many percentage points different one group is than the other. However, it's in a fixed time frame. And you should use this when your audience is clinicians or policymakers who really want to know how much extra risk is added or it's reduced per 100 patients, right? So for 100 people, your risk difference can tell you really quickly, how many people would be affected by a change that you're proposing or something like that. Risk ratios are great when you're comparing the relative risk of an outcome between two groups over that fixed period. So it relates them into a nice, easy number where 1 is equal risk between the two groups. Less than 1 means one group has less risk than the other, and more than 1 means one group has more risk than the other. So that's really easy to know. And it's a very low inference number, but it's not as absolute an effect size as risk difference. Odds ratios are really useful when you're doing a case control or retrospective cohort analysis, and when the outcome is pretty rare, generally less than 10% of the time. It's a little more robust against unusual situations, but when the outcome is very common, odds ratios can overestimate the impact compared to risk ratios. And one thing that's nice is that this is the product of logistic regression values, so that can be very helpful for looking at odds-related phenomenon in your studies. Your hazard ratio is great when you're analyzing time to event, survival analysis, right? When time and risk are related, and when the outcome could happen to different people at different times, that can be really useful. And you want to account for censoring in different follow-up times and things like that. This can be really a useful way. And it's also a very intuitive number. So in 6 years, your hazard ratio is 1.5 times greater of developing cancer than people in some other group. Let's look at how TriNetX represents these numbers now that we know how they work. So here's your measures of association window. Whenever you run an outcome in TriNetX, it's going to tell you that this risk box over here, for any given outcome, for any given cohort in this particular outcome, Alzheimer's disease, is patients with the outcome divided by the total number of people in the cohort. So in the no statin group, 2,500 people get Alzheimer's and 2,547, and you divide that by 741,966, and that gives you 0.343, give or take, considering that some of these things are rounded. A very, very easy number to compute. This is just the risk in the population. Super simple. And you can see it just kind of tiles across that way. It's also going to generate that risk of outcome measure for you. And I strongly recommend recreating this graph later because, number one, it's a little ugly in TriNetX. They are using have to do this at scale, so their graph production software maybe is a little off the shelf. But I strongly recommend redrawing these with better sizing on the y-axis, on the x-axis. In this case, I would probably put it between 0 and 2 or something like that, or 0 and 1. Because right now it just looks like there's not much of a difference, even though the actual differences are, the risk difference is 0.129%. So you can see that these values are just represented on this thing. So risk ratios, though, are a very useful number. Here's risk ratio over here. You can see we talked about risk difference. This is just 0.343 minus 0.214 is 0.129. And it runs a z-test on this, and we'll talk about this in just a second, actually. But let's talk about risk ratios. Risk ratios are just risk of A divided by risk of B. So if you're looking at no statin divided by statins, that's 1.605. Not really rocket science. Again, going back to risk difference, is that risk of A minus risk of B generates this number down here. And then it gives you a z-test comparing the two. So how different are these two values based on all of the other factors that we're looking at? And that z value here, 14.959, is just like a t-test value, and it produces a p-value that's less than 0.0001. So that's your statistical significance. And I strongly, strongly, strongly recommend for these studies reporting your 95% confidence intervals. For those who need a little refresher, basically, if you ran this, if you just click the run button 100 times in TriNetX, 95 of those times, your values would be between 0.112 and 0.146. And that is good in terms of your risk difference. And that's good because it means that we're centered in a pretty narrow range. If it was like between 0.112 and 20, that means there'd be a lot of statistical variance in there that we probably can't account for very, very effectively. Same with risk ratio. The 95% confidence intervals help you understand how narrow, how reliable your data are. In this case, it's smack dab 1.6 is smack dab in the middle of 1.5 and 1.7. So it's likely if we ran this 100 times, the value would be in a pretty similar range of values. There's your risk difference box there. Odds ratios are similar. They can be thought of similarly as we talked about a moment ago, but the math is a little more, we're going from first grade math to third grade math. But basically, your patients in cohort 1 with the outcome divided by patients with in cohort 2 with the outcome, you divide those by each other, and then you divide that by the patients in outcome 1 without the outcome and patients in cohort 2 without the outcome. And what this produces for you is your odds ratio. It's the likelihood of an event occurring right there. And it's sometimes similar to the risk ratio, though sometimes the values can be a little different. Here's the math for that if you want to just pause and visualize this really closely. But you can see 2547 divided by 1588 divided by their relative cohort amounts, 0.003432 divided by 0.002136. You can see, by the way, that these are actually the risk ratios too, so you can just shorten it by dividing the risk ratios pretty quickly. If you want to simplify your math, equals 1.607. So basically, risk ratio 1 divided by risk ratio 2 gives you odds ratios as well. So that's why the numbers wind up being quite similar between the two. Just some notes, even if you get a small result like 0.13, because we're working at such large scales, at the population level, I've had biostatisticians say to me, oh, 0.13% is clinically meaningless. I'm like, yeah, clinically, but we're not talking about one clinic where you see 10,000 people in a year. We're talking about 70 hospital systems across the US that see tens of thousands, if not millions of people every single year. At the population level, 0.13% can be huge. If these numbers held true, which we've run them since, and they're slightly different, but not too far off in terms of scale. If there are 13 million statin patients in our system and 0.0013% of them, 0.0013 got statins and had a lower risk of Alzheimer's, that'd be 16,900 people. The lifetime cost of Alzheimer's care is like $400,000 according to to Medicare, on top of normal healthcare costs. And if you multiplied that by 16,900, you'd wind up with $6.76 billion that we could save. And we could use that for hospice care. We could use that for reducing caregiver burden. We could do all sorts of important stuff with that. It's a drop in the bucket, about 2% of Medicare overall across every year's Medicare budget. But, 2% is 2%, right? We can use that 6.76 billion. That can hire a lot of people. It can pay for a lot of goods. It can pay for a lot of medications. And most medical plans cover 100% of generic statins. So it's low cost to no cost to the patient, pretty much. Not saying we should just start, and this is definitely not advocating for giving people statins to prevent Alzheimer's. However, unless there's some future research that indicates that that's a good idea. However, this does indicate that if they need it, it won't make them higher put them at a higher likelihood of developing Alzheimer's, which is really important, because I have heard from physicians that sometimes patients with stroke or dementia or other kinds of neurological conditions will sometimes be worried about the impact of statins on their memories. And in this case, we can say that it's not more likely to cause them. It's in fact possibly less likely to cause them or help protect against or buffer against Alzheimer's. Bearing in mind, though, that our cohort, as we've developed it, is full of very healthy people with really no comorbidities for Alzheimer's. We've excluded everything else. It's not a natural group of people, because our goal was to answer a specific question about the relationship of this medication with a particular negative outcome, a particular adverse event that we would want to prevent, if at all possible. So those are some notes on outcomes analysis and measures of association. With your outcomes analysis, you also get, I always recommend turning on Kaplan-Meier and time-based tests, because you want to see how much time plays a role in these outcomes. Do you have your time scale correct? As we talked about earlier, that's an important issue to understand. And also, it'll produce a hazard ratio for you, which is a very robust and useful metric for things as well. So let's go through this a little closely. I just want to be clear. Survival does not mean mortality. In epidemiological terms, survival refers to the absence of a particular outcome in a group of patients. Survival just means time to event. I talk to medical students a lot of times where they're like, well, wait, why are so many of my type 2 diabetes patients dying in every single one of my outcomes? And I'm like, well, because they're not dying, it doesn't mean they're not surviving. It means that the event that you're looking at, the outcome you're looking for, occurred to them at that time. It means that within the time frame you've defined, those people are seeing your outcome. You can see here, it'll tell you the percentage of people in your outcome. It's pretty much the inverse of the numbers that you saw a little while ago in the measures of association. This is think of it as the probability of not having the outcome. There's your survival probability on the y-axis, and the Kaplan-Meier analysis is directly related to the graph, the curve itself. So you want to understand how to read this. Basically, at the top of this curve, 100% of people are healthy. Down here at the bottom of the y-axis at 0, that means every single person got the condition that you were looking for. Then on the x-axis, this is 0 days and 7,000 or however many thousands of days that your study is scoped to go out. So that means at 3,000 days, this percentage of the people have developed Alzheimer's. It's a very small number. We would have to zoom in on it. It actually doesn't help to have the y-axis generically generated like that, which is why you should use my TriNetX publication toolkit to make a survival curve that better represents your data. So it's the odds of event occurring in your tool, in your study, and days after the index event. Those are the relationship. And it's percent of your cohort without the outcome. Just to drive this home a little more to understand what survival looks like. Imagine I gave you 5 balls. This is the only image of cans on a fence that I could find that was so not endorsing Shine or Bach, never would. But imagine I give you 5 balls and you started throwing them at these cans. So you hit the first one, you missed the second one, you hit the third one, and you hit the fourth one. So out of 5 balls, after 5 throws, you have 1 can left. That means your survival rate is 25% in the 5 throws that I gave you. So 1 survival per 25%. So yeah, again, just drive that home. Shows the percentage of people without the outcome over the number of days. This is not the number of people who develop the outcome. So at the beginning, every survival graph starts with everybody not having the event. That's the day of the index event. And either the index event occurs on that first day between 0 and 1, or after 1 and all the way down the line to that many days out. Here's a real world example of famotidine and aspirin for COVID-19 outcomes versus no famotidine and aspirin. And you can see that the aspirin and famotidine group did a lot better. A lot fewer people developed this COVID-19 severe outcomes than the people who didn't get it. So that could indicate that. And especially you can see the steep drop. So in the first 40 days or so, those outcomes, it really helped to prevent those outcomes. And then it trails off. There's not a lot of new cases afterwards out to 300 days. So there could be something else going on, or maybe it just takes some percentage of people longer to develop those conditions. But you can see here that this graph can be very, very useful in seeing how long it takes for roughly 50% of the population to develop these groups versus the others. So it's very interesting. So you might also decide to cut your study at 40 days to capture that group of people that drop, but leave these people. Who knows what's going on with them? Maybe they're not people of interest and there's some other event occurring. You can see these little flat drops here indicate that the individual cases become fewer and fewer and fewer over time. So capturing 40 days, you get this nice smooth curve indicating lots and lots and lots and lots and lots of cases of whatever it was, maybe mortality, all the way down till it flattens out at about 40 days forward. So this group, without changing their numbers too much, probably could have cut their analysis at 40 days and been just fine. Or you could even cut it at 180 days and gotten almost all of your value for the study and have a much more temporally linked series of events. Other metrics you're going to get with your TriNetX, with your Kaplan-Meier analysis is a log rank test. This is going to compare the percent of survival, the percentage of people in both groups at the end of your value to see if there's a statistically significant difference between the two. It's a chi-square. So the chi-square tests the consistency or the likelihood that they're both from the same pool. And in this case, they're statistically significantly different, which indicates that that there's a difference between the number of days, weeks, months, years that it takes for these two groups to develop Alzheimer's. It's always going to be 1 degree of freedom when you're comparing two groups because it's n-1, or j-1 for degrees of freedom. And your p-value is the alternate, tests the hypothesis of whether the curves are the same for groups 1 and 2. In this case, they are not. Hazard ratio is super useful. It is the comparison to the rate at which patients in a cohort experience an outcome for the first time. Compares how quickly 2 groups of people experience an event over time. For example, if it's 2, it means that 1 group is experiencing the event at twice the rate of the other group in that exact same time frame. And as always, pay attention to your 95% confidence interval to see how reliable your data are. Proportionality is an additional tool that it's really important because the hazard ratio, the Cox proportional hazards model that produces this ratio, assumes what they call proportionality. That is, the factors that are impacting things are stable over time. And so if something's statistically significant, in this case, the factors, there's some set of factors, probably multiple factors impacting this that are not the same for both groups. It could be age impacts one cohort much more than the other, or some subset of other factors. So our assumption of proportionality for the hazard ratio analysis and the Cox proportional hazards model is not there. So that's actually not great for using the hazard ratio in there because a bunch of other stuff is impacting things over this length of time span. So if we cut our time span, it might restore our ability to assess the proportionality and then make it so we can use this, but that would require probably trimming down the number of weeks or months or shrinking the pool of people. Just to make things even more confusing, sometimes survival does mean death. When your outcome is mortality, it means that your risk of outcome, that your survival rate here indicates actual survival of people. So if you're talking about death or mortality, you're going to also be talking about that. So it's something to think about. Also, just bear in mind for mortality, looking at these graphs where the people die, if you've got it going out this far, this just means that your groups are like 7,000 days older than when you started. And means people are much, much more likely to pass on over time, especially if their ages are distributed in that way. And you can see there, over that time, you're 1.486 times more likely to pass away if you're in one group than the other. Last, I'm just going to touch on this briefly, but the number of instances test allows you to include either each date of occurrence. Like, for example, let's imagine you had people in a hospital and you wanted to know, did they get 10 daily doses of antibiotics or 14 individual instances? This can help you find out, number one, how many times they were given a particular medication, but also whether how frequently these doses were given. So you can adjust it to figure out number of instances. It's not always that useful outside of pharmacological uses, but it can be useful on certain circumstances to help you out. The graph looks something like this, and you can see it gives you a nice t-test comparing whether the instances between the two groups are different as well. And you can see here the dates out from there that we'll be looking at. So based on all of this, here are our hypotheses. Our statins not associated with any change in likelihood of development of Alzheimer's. That's false, because it is associated with a lower likelihood of developing Alzheimer's in the long term. So that's something you really need to think about. Finally, we're just going to review a couple of things. Outputting your data to share. This is very useful, and I want to call attention to it. So when you've got your results over here, you can actually go and export all of your results in a couple of different ways. This is super handy because TriNetX is a dynamic system. If you come back later and have to rerun your outcomes, you might draw a different pool of people. You might find that there are more people in your pool than you initially reported, and you're going to be in a situation where you can't exactly replicate your earlier findings. This has actually happened to students before. As new networks come to TriNetX and bring new data, it becomes harder to make sure that your data is identical each time. So when you are exporting all, you can choose to export all of your results, 1A and 1B from each outcome. And then you can choose to either export it as individual files, which can be very useful in working with my TriNetX toolkit that I will be sharing out more broadly later. And you can also download the report as a Word doc, which is really great for just locking in all of your stuff. So this makes it easy to send your research results around to mentors or research partners, because everything, all the numbers, all the metrics, all the variables you used in your analysis are going to be captured in there, along with all the codes you used, so other people can check them and make sure that they're accurate. You can send them to a specialist and have them check and see whether you're using the correct CPT codes or not. You can log that snapshot for later and make sure that you can refer back to it over time. And you don't have to keep referring to the website and logging in and everything like that. You can just have a nice little paper that you can copy and paste into Word documents or something like that. What's included in the Word doc? It outputs all the criteria for your cohorts. It outputs the logic of the design of the cohorts, which is super interesting. Here's all of the ICD-10 codes we used as our exclusion criteria, which can be super useful. It includes your risk analyses, your measures of associations as well, right here in a nice format that's very easy to read. And appendixes A through C include all of your cohort definitions and your setup variables and all sorts of stuff like that. So you can kind of save this. You could submit it to a journal as evidence of your analysis and the structure of your analysis, all sorts of things like that. And you can download the CSV files as well using the same. So when you download the individual files, it'll actually output things like your CSV file that includes all of your survival curve data. And then you can use my TriNetX survival curve viewer to redraw it with better axes or more accurate axes and things like that. It can be super, super useful to do this. So downloading these also creates little outcome results. So each of your outcomes tables gets exported into a little Excel sheet, which you can then also import into the TriNetX toolkit. That's it. It has been quite a ride. I want to thank you for joining today. If you got any questions, feel free to email me, let me know. And I'm always happy to work with folks on their projects as well. Next time, we're going to talk about the Cox proportional hazards model and the time on treatment and treatment lines tools, which will be a little shorter, but I think will be a good way to expand your repertoire of analyses within TriNetX and beef up some of your analyses as you get them ready for publication as well. So thank you so much. I will see you at the next one. And please feel free to contact me and let me know if there's anything I can do for you. All right. Have a great day and wherever you are, whenever you are. Thank you so much.